Hello and welcome. Today we're diving into one of the most important and honestly one of the weirdest ideas in all of modern physics, the photoelectric effect.
For centuries, it felt like the debate was over. Light's a wave, case closed. It moves through space, kind of like ripples on a pond. But then, a pretty simple experiment started asking a really awkward question. What if that's not the whole story?
And this wasn't just some small detail they got wrong. The results from this one little observation made absolutely no sense. And trying to figure it out, well, that sparked a revolution that completely flipped our understanding of reality on its head.
So, here's how we're going to crack this case. We'll start with that puzzling observation, then look at the wild idea that light is a particle. We'll need to define some new concepts, check out Einstein's brilliant equation that ties it all together, and finally, look at the ultimate proof that sealed the deal.
Okay, so the experiment itself sounds super simple. You shine a light on a piece of metal and poof, it can knock electrons right off the surface. We call those photoelectrons. The setup was easy, sure, but the results were just baffling.
So the thinking from classical physics was totally logical. If light is a wave, a brighter, more intense light is just a bigger, more powerful wave. So a bigger wave should hit those electrons harder and send them flying off with more energy, right? Makes perfect sense.
Except that's not what happened. Not at all. What experiments actually showed was that a brighter light didn't give you higher energy electrons. It just gave you more of them. The energy of each electron had nothing to do with the brightness. Instead, it was completely tied to the light's color, or to be more specific, its frequency.
And this is what was so mind-bending. This analogy really nails it. Imagine you're in a canoe. Giant, monstrous waves roll by and do nothing. But then, a series of tiny little ripples comes along and launches you into the sky. It made no sense. It broke all the rules. Something about our understanding of light was fundamentally wrong.
So how do you even begin to solve a puzzle like that? When the old wave theory completely fails, you need a new idea, a really radical one, and it came from a place nobody was really expecting.
The first piece of the puzzle came in 1900 from Max Planck. He was working on a totally different problem and came up with this idea that energy isn't a continuous flow. He said it comes in little chunks, or quanta. 5 years later, a young patent clerk named Albert Einstein took that idea and ran with it. He made a huge leap and proposed that it's not just that energy is emitted in packets, light itself is made of these little energy particles.
Now, this idea that light is a particle, well, it was so new it needed a whole new dictionary to go with it. So to really get what Einstein was saying, we've got to get a handle on a few key terms that became the building blocks of this new quantum world.
First up, the big one, the photon. This is what Einstein called a single particle of light. So instead of a smooth, continuous wave, you have to imagine light as a stream of tiny little energy bullets. And the energy of each bullet is determined by its frequency.
Okay, next we have the work function. You can think of it like this. Every metal holds onto its electrons pretty tightly. The work function is the minimum amount of energy it takes to prime one of those electrons loose. It's basically the exit fee an electron has to pay to leave the surface.
Which leads us directly to the threshold frequency. Because a photon's energy is tied to its frequency, there's a minimum frequency, a specific color of light, that has just enough energy to pay that exit fee. If your light's frequency is too low, you can shine it all day long, make it as bright as you want, and absolutely nothing will happen.
So once we have these new definitions, everything starts to click into place. And Einstein wrapped it all up in a single, beautiful, and incredibly powerful equation that just solved everything.
This is it. It looks so simple, right? But don't let that fool you. This little equation represents a monumental shift in how we see the universe. It's the key that unlocked the whole mystery.
Let's break it down. The incoming photon arrives with a certain amount of energy, which is h times f. Then it spends some of that energy, the work function phi, just to pop the electron out. Whatever energy is left over becomes the electron's kinetic energy, how fast it moves. And just like that, it explains everything. Brighter light just means more photons, so more electrons get knocked out. But if you want a faster electron, you need a photon with more energy, which means a higher frequency, a bluer light.
Now, an idea this revolutionary couldn't just be a neat explanation. It needed cold, hard proof. And ironically, that proof came from someone who was dead set on proving Einstein wrong.
Let's bring in our final character, Robert A. Millikan. He was a master experimental physicist, and he was really not a fan of this whole photon business. He thought it was, a bit out there, and he was determined to run the experiments that would put the idea to rest for good.
So for years, Millikan painstakingly built this incredibly precise experiment. He carefully shined different colors of light on the metal and measured the exact energy of the electrons that came flying off. And when he plotted all his data on a graph, he found a perfect, straight-line relationship. It was exactly what Einstein's equation predicted. In trying to disprove it, the great skeptic had accidentally become its greatest validator.
You have to love the poetry of it. Millikan himself, the guy who doubted it all, had to conclude in his own paper that this equation had to be, quote, one of the most fundamental and far-reaching of the equations of physics. You can almost hear him admitting defeat and awe.
And that was it. That was the nail in the coffin. Millikan's incredible work was the hard data that proved light really does behave like a particle. And it was for his explanation of the photoelectric effect, and kind of surprisingly, not for relativity, that Albert Einstein won the Nobel Prize in Physics in 1921.
So we end up in this bizarre new reality. Light is somehow both a wave and a particle at the same time. It's a cornerstone of quantum mechanics, this idea of wave-particle duality. And it just makes you wonder, doesn't it? If something as fundamental as light can have a secret identity, what else about our universe is just hiding there, waiting for us to ask the right question?